Hello, and welcome back to the Midnight Scientists. Drift with me now into a realm where silence is not an absence, but a presence. Close your eyes and listen for the quiet hum of the cosmos. It's the sound of a story that has been told for almost as long as there has been a universe to tell it. This story isn't written in words or etched on stone. It's carried on the most ephemeral and persistent of all messengers, Starlight. Chapter 1: The First Whisper of Light. Imagine a single point of light in the vast, inky blackness above you. It's a distant sparkle, a fragile glimmer, a pinprick of frozen fire. We see this light. We feel its gentle pull on our imagination, and for a moment, we are lost in its silent beauty. Poets have written about it, lovers have wished upon it, and for all of human history, it has been a comforting, constant presence in the darkness. But what if that familiar glimmer is not just a light? What if it's a whisper? A conversation that began millions of years ago, finally arriving to tell you its secrets. Starlight is one of those things so familiar, we rarely stop to consider its true nature. It's not magic, but it is science at its most elegant. At its heart, starlight is pure energy, a specific sliver of the immense electromagnetic spectrum. Think of the warmth from a campfire on a cool night, the faint hum of a microwave heating your mug, or the invisible streams of energy that carry a Wi-Fi signal through your home. These are all part of the same vast family of energy, invisible to us in their raw form. But light, the light we can see with our own eyes, is a tiny and precious note in that cosmic symphony, a single chord played by a distant sun. Visualize for a moment the electromagnetic spectrum as an endless ribbon of frequencies. At one end, there are the long, languid waves of radio energy, stretching for kilometers. At the other, the frantic, high-energy pulses of gamma rays and X-rays, each shorter than an atom. In the middle, nestled between the gentle warmth of infrared and the burning pulse of ultraviolet, lies the sliver of visible light. This is the part of the ribbon our eyes evolved to see, precisely because our own star, the sun, radiates most abundantly within it. This tiny slice of the rainbow is what we perceive as the light of the stars. But a star is not a bedside lamp, glowing with a simple, uniform warmth. It is far more complex, a furnace that radiates across the entire spectrum. The light that reaches us is a blend of all these frequencies, but what we see most clearly is determined by a star's mood, its temperature. This is where the quiet wisdom of color comes into play. A red star is a star in a more meditative state. Its surface, while still unimaginably hot by our standards, perhaps 3,000 to 5,000 degrees Celsius, is cooler than most. These stars, often smaller and long-lived, emit most of their light in the red and infrared parts of the spectrum. They glow with a soft, gentle orange or ruby hue, burning their fuel slowly and patiently, like a fire that will last for eternity. Imagine drifting toward one of these quiet giants, a world of soft red warmth, its light caressing the empty blackness around it. At the other end of the scale are the fiery, flamboyant blue stars. These are the celestial sprinters, massive and intense. Their surfaces can blaze at temperatures over 30,000 degrees Celsius, pumping out a staggering amount of energy. A star like this shines with a brilliant, icy blue or even a violet light. It lives fast and burns out spectacularly, often in a matter of a few million years. These stars are a brief but dazzling flash in the cosmos, a brilliant, cold fire against the void. Our own sun, a calm and steady presence, sits comfortably in the middle of this scale. It is a yellowish white star with a surface temperature of around 5,500 degrees Celsius. Its light is a balanced blend of all the visible colors, which is why we perceive it as a gentle golden white. The next time you feel its warmth on your face, remember that this sensation is the result of a physical process so elegant it has been telling stories for billions of years. The color of a star is more than just a pretty picture. It is a cosmic thermometer. A red star is cooler. A white star is hotter. A blue star is hotter still. This quiet, reliable signal tells us everything we need to know about a star's surface temperature, its energy output, and its place in the great cosmic story. No need to fly a spaceship with a thermometer. The light itself carries all the information. But this elegant rule has a quiet complexity. While a star radiates light in a continuous, rainbow-like spectrum, that spectrum is not perfectly smooth. It is interrupted by thin, dark lines, like a barcode etched in black ink. These are the whisperings of atoms. They are called absorption lines. Each one is a message, a fingerprint of the very elements that make up the star. They tell us what the star is made of, what gases float in its outer layers, and what stories those elements have to tell.
Chapter 2: The Silent Journey of a Photon. Drift with me now, away from the warm surface of the star and into the vast, lonely silence of space. Imagine a single photon being born deep in the star's core, a tiny, tireless packet of light energy with no mass, no charge, and no plans of ever stopping. It begins its life in a place of unimaginable chaos, a furnace of roaring plasma, a seething ocean of heat and pressure. At first, this little photon's journey is anything but a straight line. It is a slow, frustrating dance. It is born in the core and immediately collides with an electron. It is absorbed, then re-emitted in a random direction. It bumps into a proton, a helium nucleus, another photon. It bounces and ricochets in a drunken, zigzag path, like a lost firefly in a crowded forest. The journey from the star's core to its surface can take thousands, even millions of years. It's a staggering thought, isn't it? By the time a single photon of starlight finally breaks free, begins its cosmic voyage, entire civilizations may have risen and fallen on a distant, orbiting rock. Once it finally escapes the star's outer layers, the photon enters open space, a realm so vast and empty it's almost impossible to describe. Imagine the silence, the sheer, profound emptiness. If you could take an average cubic meter of interstellar space, you would find only a handful of particles, perhaps a stray hydrogen atom or a wisp of dust, but mostly it's just vacuum. This emptiness is perfect for a photon. After all that bouncing and wrestling inside the star, it now gets to stretch its metaphorical legs and coast in a straight line, uninterrupted at the ultimate speed limit of the universe. This speed, nearly 300,000 kilometers per second, isn't just fast. It is the very definition of speed. Nothing outruns light, and nothing ever will. At that velocity, a single photon can circle the Earth over 7 times in 1 second. But photons aren't just zipping around our planet. They are crossing the gulfs between stars and galaxies, often for millions or even billions of years. It is not a quick commute. Once in space, photons do something rather lovely. They stay the course. Unless acted upon by gravity or matter, they travel in perfectly straight lines. They don't get tired, they don't slow down, they don't age in the way we understand time. In fact, from the photon's point of view, time doesn't pass at all. For us, the light from a star might take 1,000 years to reach Earth, but for the photon, that journey is instant. It is as though it blinked into existence in a star and blinked out again in your eye without ever noticing the eons in between. But while space is mostly empty, it's not completely empty. Along the way, a photon might encounter an obstacle, perhaps a stray particle, a cloud of gas, or a wisp of cosmic dust. When they do, a few things can happen. The photon might be scattered, getting slightly off its quiet, straight path. It might be absorbed entirely, never making it to its original destination. Or, in most cases, it might pass through unbothered, especially if it's energetic enough or traveling through clearer regions of space. Cosmic dust might sound romantic, like something glittering in the void, but it's actually a nuisance for light. These tiny grains, often made of carbon, silicon, and ice, float through space like microscopic snowflakes. In dense regions, like the glowing gas of a nebula or the crowded disks of galaxies, they can block or scatter light, especially the shorter, more energetic blue wavelengths, which is why distant galaxies can sometimes look a little reddish. Their blue light has been scattered away, leaving only the longer, redder wavelengths to reach us. It's the same reason a sunset on Earth is red. Our atmosphere scatters the blue light, painting the sky with the lingering reds and oranges. And even when photons dodge all the dust and debris, they still have another obstacle to contend with: gravity. Now, gravity doesn't tug on light the way it does on objects with mass, but Einstein's general theory of relativity tells us that gravity isn't just a force, it's a curvature, a warping of space-time itself. And photons, despite having no mass, still follow the curves. Imagine placing a heavy bowling ball on a taut trampoline and watching how the surface dips. Now roll a marble past the bowling ball, and you'll see it veer along the curve. That's essentially what happens when light passes near a massive object, like a star, a galaxy, or a black hole. Its path bends, not because it's been pulled, but because the space it's moving through is bent. This bending of light is called gravitational lensing. It's one of the more elegant and mind-bending ways the universe reveals itself. When a massive object sits between us and a more distant light source, it can magnify, distort, or even multiply the image of that background source. We've seen galaxies appear as brilliant, distorted rings, as strange arcs of light, or as multiple strange mirrored shapes, all thanks to the gentle, unseen hand of gravity bending light across the eons. Gravitational lensing is not just beautiful, it's useful. It acts like a natural magnifying glass, allowing astronomers to observe galaxies that would otherwise be too faint or distant to detect. And it also helps us map the invisible, silent presence of dark matter. Since we can't see dark matter directly, we use the way it bends light to figure out where it is and how much of it there might be. In a way, it's like watching the ripples in a pond to guess where an invisible stone might be sitting on the bottom. But for all its encounters with gravity and dust, the majority of starlight travels largely uninterrupted, and this is where the magic truly begins. because as that light crosses the universe, it carries with it a time capsule. Photons don't just illuminate, they inform. Each one that reaches our eyes or telescopes has traveled across years, centuries, or even cosmic epochs. The farther away the source, the older the light. When you look up at a star that's 500 light years away, you are seeing it as it was 5 centuries ago, when the world of our ancestors was entirely different. For stars within our own galaxy, these time gaps are manageable, dozens, hundreds, maybe thousands of years. But when we peer deeper into other galaxies, we are talking millions or even billions of years. Some of the most ancient light we have ever detected began its journey just a few 100 million years after the universe itself was born. Those photons have traveled the length and age of the cosmos to reach us, bringing stories from a time before our sun, before Earth, before any form of life we know. The night sky is a gallery of ancient portraits. But light doesn't age or degrade the way sound does. A photon doesn't grow fuzzy or tired with distance. It doesn't fray at the edges. What can happen, however, is a stretching, a subtle, slow pulling of its wavelength. As the universe expands, it stretches the space between things, and that stretching affects light too. This is cosmological redshift. Photons that began as high-energy ultraviolet or visible light arrive as a low-energy infrared or even microwaves. Their color changes not because they have slowed down, but because the space around them has gently, relentlessly stretched. This quiet redshift is one of the main ways we know the universe is expanding. By measuring how much a distant galaxy's light has shifted toward the red end of the spectrum, astronomers can estimate how far away it is and how fast it's moving away from us. The farther the galaxy, the greater the redshift. It's like hearing the pitch of a siren drop as it drives away from you, only stretched across eons of time and light. And in that instant, as a photon finally meets its end, whether it excites a molecule in your retina or bounces onto a sensor in a telescope, the journey ends. A photon that may have traveled for billions of years finally comes to rest, not with a bang, but with the tiniest of interactions. That small, silent encounter becomes an observation, a data point, a discovery, or perhaps just a quiet moment of beauty. This is how light moves through space.
This is how light moves through space, not in chaos, but in graceful persistence, unwavering, timeless, and with a quiet purpose. It's our messenger across the cosmos, the thread that connects us to the stars. Drift with me now and wonder, if a single photon can tell a story of such immense scale and time, what secrets are hidden in the full rainbow of a star's light, just waiting to be read? Chapter 3. The First Prisms. Drift with me now, back through time, to an era when the universe was not yet a place of galaxies and quasars, but a series of beautiful, unsolved puzzles. Before humans understood what a photon was, or what stars were truly made of, there was just light. Light that warmed us, illuminated our way, and showed us the world. But for most of history, we didn't know what it was. Was it a substance? A wave? A particle? A divine glow? The journey to answering that question would eventually lead to one of the most powerful tools in all of astronomy, spectroscopy. And it all began in many ways with a prism and a rather curious mind. Visualize a quiet English garden in the late 1600s. The air is still and the sun is warm. A young man named Isaac Newton has just returned from Cambridge, seeking refuge from the Great Plague. He has a simple, elegant idea: He takes a piece of glass, a prism, and with a quiet hand, he passes a single beam of sunlight through it, letting the light spill onto the far wall of his darkened room. He is not expecting magic, he is simply performing an experiment. But what he sees is a revelation. What had looked like pure, ordinary white light from the sun is in fact a hidden blend of every color of the rainbow. The prism has not created the colors, it has merely separated them. It has broken apart the light, not randomly, but in a precise, orderly way, spreading them in a smooth gradient from deep red to soft violet. This was not a party trick, it was a profound discovery. White light was not pure. It was a symphony of every color hidden within a single, brilliant note. Newton had shown that light could be broken apart into a spectrum. He concluded that light was composed of different rays, each with a different bending power. Each color bent at a slightly different angle as it passed through the prism, revealing the secret harmony held within. Newton was not just fiddling with glassware for fun. He was laying the groundwork for centuries of discovery. By showing that white light was a composition of many colors, he opened the door to a new question. What happens when light comes from other sources? What does the spectrum of a candle look like? Or a burning coal? Or a star? That question lingered in the quiet corners of scientific thought for over a century, a patient seed waiting to grow, until in the early 1800s, a self-taught genius named Joseph von Fraunhofer took up the thread. Fraunhofer was a German optician, a master of glassmaking. He had a deep, personal fascination with light. While creating better lenses for telescopes, he began to analyze the sun's spectrum with his own finely crafted prism. Like Newton, he saw the familiar rainbow of colors, but unlike Newton, his instruments were more precise, his eyes more sharp, and he noticed something odd, something that shouldn't have been there. Running through the continuous rainbow of colors were hundreds of thin, precise black lines. They were like tiny, perfect scratches on the record of the sun's light. They were not random. They appeared in the exact same place every time he looked at the sun. Even more interesting, when he looked at the light from a different source, like a flame or an artificial light, the lines changed. Some disappeared, others appeared in new positions. Fraunhofer had stumbled upon one of the universe's secret languages. Today, we call them Fraunhofer lines, and they are the invisible fingerprints of the sun. He didn't know what caused them, but he knew they were real, reliable, and deeply significant. And he was absolutely right. Those dark lines were not flaws or optical quirks. They were the silent whispers of atoms, a kind of code written in the light itself. It wouldn't be until decades later that the physical explanation would finally come to light, when scientists began to connect the dots between the realms of chemistry and light. In the mid-19th century, two German scientists, Gustav Kirchhoff and Robert Bunsen, the very same Bunsen of laboratory burner fame, discovered that each chemical element, when heated, emitted light with a unique set of bright, glowing lines, as if each element had its own glowing barcode. By passing light from a flame through a prism, they could identify which elements were present in the flame by looking for their unique spectral lines. Sodium, for example, produced a brilliant yellow line. Hydrogen had a whole series of lines in the red, blue, and violet. Suddenly, light became more than just illumination. It became information. Spectroscopy was born. Kirchhoff and Bunsen then realized that the dark lines Fraunhofer had seen in sunlight matched the bright lines produced by those heated elements. The implication was profound and humbling. The sun, that distant, powerful furnace, contained the same elements found right here on Earth. The cosmos was not made of something unknowable or alien. It was made of the same stuff, obeying the same laws. This was the start of modern astrophysics.
With this new tool, astronomers could now analyze the light from stars, nebulae, and galaxies to determine their chemical composition, their temperature, and their motion, and more. All of this came from nothing more than a bit of light broken apart and gently read. It's worth pausing to appreciate how truly bizarre this is. With a prism or a fine grating, we can analyze a flicker of light from an object thousands or millions of light years away and deduce what it is. No need to send probes or collect samples. We can read a star's autobiography from its glow.
Perhaps the most poetic side of starlight is this. It is not just the light that reaches us. It is the story hidden in that light. The glow of a fire and the fingerprint of a furnace, a continuous rainbow and a detailed barcode. A beam of light becomes a conversation. A dark line on a spectrum becomes a whisper from a faraway sun. And the next time you look at the sky, you can almost hear the universe's quiet voice asking a single, beautiful question. If light can tell us what a star is made of, what can it tell us about how that star is moving through the great dark ocean of space?
Chapter 4. The Cosmic Dance. Drift with me now, away from the static portrait of a star, and into the quiet, graceful reality of its life. A star seems like a fixed point, a serene ornament pinned to the celestial dome. But that peaceful appearance is only a surface illusion. In reality, stars are in constant, tireless motion. They spin, they orbit, they drift, and they wobble. They are not fixed ornaments. They are travelers, participants in the great galactic ballet. And while we cannot feel these motions directly, we can see them and read them through the subtle language of their light. Our trusty tool for decoding starlight, spectroscopy, turns out to be an excellent motion detector. Not only does it reveal what stars are made of and how hot they are, but it also gives us quiet clues about how they are moving. The key to all of this is the Doppler effect, a principle we can hear in our everyday lives. Imagine standing on a quiet country road as a car approaches. The sound of its engine seems to have a higher pitch as it moves toward you. But as it speeds past and recedes into the distance, the pitch drops and grows lower, fading with the miles. That sudden shift in sound isn't a trick of your ears. It is a real physical effect. When a source of waves moves relative to an observer, those waves are either compressed or stretched, depending on the direction of travel. With sound, we hear this as a change in pitch. With light, we see it as a change in color. Now, light travels in waves too, though we often don't think of it that way. When a star or a galaxy moves toward us, the light waves it emits are gently compressed, their wavelengths shortening. This pushes the star's entire spectrum toward the blue end, a phenomenon called a blue shift. When a star moves away from us, the light waves are stretched out, their wavelengths lengthening. This shifts the spectrum toward the red end, a redshift. The effect is subtle, a silent nudge on the canvas of a star's light, but it is one of the most powerful signals we can read. The amount of this color shift is directly related to the star's velocity. With instruments so sensitive they can detect motion of just a few meters per second, we can read a star's speed from across the cosmos. It's a bit like listening to the universe hum and noticing when certain notes are a little sharp or a little flat. This quiet, color-coded spinometer allows us to measure a star's motion along our line of sight, a movement known as its radial velocity. This subtle has unlocked some of the universe's most beautiful and mind-bending truths. It's how we know that many stars are not alone, but are part of binary systems, locked in a gentle gravitational dance around an unseen partner. Their spectra wobble back and forth, a rhythmic blue shift and red shift, telling us of their silent, endless ballet. The Doppler effect also revealed something even more elusive, the presence of exoplanets. When a star has one or more planets orbiting it, it doesn't sit perfectly still. It responds to the gravitational pull of those planets by moving in a tiny circular path of its own. This creates a minuscule Doppler shift in the star's light, a back and forth wobble that we can detect with our most sensitive instruments. We don't see the planets directly, but we detect their presence by the way they tug on their stars, altering the color of starlight in a whisper that only careful eyes can hear. But stars do not only move directly toward or away from us, they also move across the sky in a sideways drift known as proper motion. This is the gradual, years-long change in a star's position as it travels across the celestial sphere. To measure this, astronomers take incredibly precise images of stars years apart and patiently compare their positions, charting a star's slow, grand pilgrimage across the galaxy. To understand a star's true motion through space, we must combine its sideways drift, proper motion, with its forward or backward motion, radial velocity. One tells us how a star moves across our field of view, the other tells us how it moves toward or away from us. Together, they give us a full three-dimensional picture of a star's journey through the cosmos. And there is even more to read in the quiet symphony of starlight. Spectroscopy can also tell us if a star is spinning. When a star rotates, different parts of its surface are moving in different directions. The side rotating toward us is moving slightly closer, so the light from that side gets a tiny blue shift. The side rotating away from us is moving slightly further, so its light gets a redshift. The result is a kind of gentle stretching of the star's spectral lines. They broaden out, smearing from sharp, narrow lines into fatter, fuzzier ones. By analyzing how much the lines are broadened, astronomers can estimate how fast the star is spinning, a silent record of its inner energy. In the end, what seems like a quiet, steady point of light is actually bursting with unseen motion. Stars wobble, spin, pulse, and orbit. They drift through space, rotate on their axis, and sometimes gallop through the galaxy in high-speed arcs. And all of it can be seen, measured, and understood through the spectrum of their light. Starlight becomes a kind of celestial dance chart. It doesn't just tell us what stars are, it tells us what they're doing. The gentle shift of a spectral line, the broadening of a feature, the rhythmic pulse in a datagram. These are the footprints of motion, written in light. They are the whispers of a cosmic dance, echoing through time and across space, waiting patiently to be read. And it is this dance, this grand, slow ballet of celestial bodies, that has led us to one of the most remarkable discoveries of our time, that the silent sky is not empty, but is teeming with distant, hidden worlds.
Chapter 5: The Search for Distant Worlds. Drift with me now and wonder. If a single star is a universe of information, what can we learn when we watch its light for the merest, most subtle flicker? Imagine looking up at a star hundreds of light years away and somehow knowing that a tiny planet is circling it. Not because you've seen the planet directly, most are far too small and faint for that, but because of the slightest, most delicate changes in the star's light. It's like noticing a moth passing in front of a distant floodlight from across a vast, empty field. It seems impossible, and yet, astronomers have found a way to do just that. With the help of light, they've discovered thousands of distant worlds orbiting stars beyond our own. These are exoplanets, planets that live in solar systems other than our own. And while they were once the stuff of science fiction, they've now become one of the most vibrant fields in astronomy. Today,
we know of over 5,000 confirmed exoplanets, and each one tells us something new about what is possible in the universe. So how do we find them? How can a planet, which doesn't emit its own light, give itself away from such an enormous distance? The answer, as always, lies in starlight. One of the most effective techniques is called the transit method, and it's surprisingly intuitive. Picture a star as a big, glowing disk. If a planet happens to pass directly between that star and our vantage point here on Earth, it blocks a tiny bit of the starlight, just a sliver. But that sliver can be measured. The effect is called a transit, and it causes a temporary, minuscule dip in the brightness of the star. The dip in light is incredibly small, usually less than 1% of the star's total light. But if it happens repeatedly at regular intervals and with a consistent pattern, it is a strong sign that a planet is orbiting the star. It's like watching a clock whose glow flickers for a moment at a precise time every day. From the depth and shape of the dip in light, astronomers can calculate the size of the planet and the length of its orbit. A shallow dip might mean a small rocky planet like Earth. A deeper dip could indicate a larger gas giant like Jupiter. And if the transit lasts longer, the planet may be farther from its star, taking more time to cross its glowing face. The beauty of the transit method is that it doesn't require any complex imaging of the planet itself. All it needs is a reliable stream of starlight and a very sensitive detector. Space telescopes like Kepler and TESS have used this method to great effect, monitoring hundreds of thousands of stars and watching for those subtle, telltale dips. But the transit method has its limitations. It only works if the planet's orbit is aligned just right so that it passes between us and the star. If the orbit is tilted even slightly, we might miss the transit entirely. That's why the method works best when applied to large numbers of stars, casting a wide net in hopes that some planetary systems happen to be edge-on from our perspective. To complement the transit method, astronomers also use another powerful technique, the radial velocity method, sometimes called Doppler spectroscopy. This method relies not on the dimming of starlight, but on its shifting. As a planet orbits a star, both objects actually orbit a common center of mass. For a massive star and a small planet, the center is located very close to the star's center, but not exactly at it. That means the star moves too, just a little, wobbling back and forth in response to the planet's gravitational tug. This motion affects the star's light. When the star moves toward us, its spectral lines shift slightly to the blue. When it moves away, they shift to the red. This is the Doppler effect at work. By measuring these tiny shifts, sometimes just a few meters per second, astronomers can detect the wobble caused by an orbiting planet. These shifts create a wave-like pattern over time, each peak and trough marking a point in the star's tiny orbit. From this wave, astronomers can calculate the mass of the planet and how far it is from its star. Combining both methods can be particularly powerful. If a planet is detected by both transit and radial velocity, we get a wealth of information. The transit gives us the planet's size, while the radial velocity gives us its mass. Together, these allow us to calculate its density, which tells us whether it's a rocky, terrestrial world, a gas giant, or something in between. This is how we've discovered some truly remarkable worlds: hot Jupiters that orbit their stars in just a few days, super-Earths with twice the mass of our own, and even planets in the habitable zone, the region where temperatures might allow liquid water to exist. And as instruments improve, we're beginning to study the atmospheres of exoplanets too. During a transit, a tiny fraction of the star's light filters through the planet's atmosphere before reaching us. That light picks up the spectral fingerprints of the gases in the atmosphere, revealing their composition. This method, called transmission spectroscopy, has already allowed scientists to detect elements like sodium, potassium, and water vapor in exoplanet atmospheres. These detections are preliminary, but they are incredibly exciting. They open the door to the search for biosignatures, chemical signs of life in the atmospheres of distant worlds. Space telescopes like Hubble and the James Webb Space Telescope are equipped with the tools to perform this kind of analysis. Webb in particular was designed with exoplanets in mind. Its infrared capabilities allow it to peer into the hazy atmospheres of distant worlds and detect the faintest traces of chemical signatures. All of this, planet sizes, orbits, masses, compositions, comes not from photographing the planets themselves, but from reading the subtle changes in a star's light. It's a game of cosmic inference built on careful observation and patient decoding. And light, once again, is the hero of the story. Perhaps the most profound part of this journey is what it implies. If our sun is just one star among billions, and if exoplanets are common rather than rare, then the universe is likely teeming with worlds. Icy ones, fiery ones, gaseous giants, rocky twins, and maybe, just maybe, life-bearing planets not so different from our own. And we're finding them not with starships or landers, but with photons, with the quiet, steady stream of light that travels across the void, carrying secrets and signatures, waiting patiently to be understood. A planet may cast only the faintest shadow on its star, or tug ever so gently at its light. But for those who know how to read it, that's more than enough. And with that knowledge, we now have the keys to unlock a deeper, more profound story, the chemical history of the universe itself.
Chapter 6: The Alchemical Universe. Drift with me now to a time, before galaxies had settled into their elegant spirals, and before the periodic table had more than just a few names on it. What would you find? A vast, expanding sea of incredibly simple matter. Just minutes after the Big Bang, the universe was filled with a scorching soup of fundamental particles, mostly hydrogen and helium, with a whisper of lithium. By our standards, it was a chemically boring universe. But what followed was nothing short of cosmic alchemy. Over billions of years, the universe transformed that bland hydrogen and helium mixture into a rich periodic table of elements: carbon for life, oxygen for water and iron, blood and skyscrapers, silicon for sand and circuits. And astonishingly, we know this entire transformation happened not because we've flown to distant galaxies or scooped up samples from ancient stars, but because of light. Starlight, filtered through the lens of spectroscopy, tells the whole story of how the universe built its own complexity, one atom at a time. The tale begins with gravity. Over time, tiny fluctuations in the density of the early universe allowed vast clouds of hydrogen and helium to collapse. As they did, they formed the first stars, massive, hot, and short-lived. These were likely what we call population 3 stars, theoretical metal-free stars made almost entirely of hydrogen and helium. We have never observed them directly, but their existence is inferred from the chemical signatures we don't see in the oldest known stars. These first stars were the universe's original fusion reactors. Inside their cores, under unimaginable pressure and temperature, hydrogen atoms were fused into helium, and in the most massive among them, the fusion continued. Helium into carbon, carbon into oxygen, oxygen into neon, and eventually into silicon and iron. Each stage released energy, fueling the star and fighting against the inward pull of gravity. But once a star starts making iron, the story changes. Iron is a dead end, energetically speaking. Fusing iron doesn't release energy, it costs it. When iron builds up in the core, the star runs out of fuel and collapses under its own weight. This collapse happens fast, catastrophically fast. In a matter of seconds, the core implodes, rebounds, and triggers a massive explosion, a supernova. And it is in these fiery death throes that some of the most precious elements in the universe are forged. Gold, uranium, lead, and other heavy elements are created in the chaotic burst of nuclear reactions that occur during these explosions. The star, once a giant furnace, becomes a chemical fireworks show, scattering newly forged elements out into the cosmos. These enriched gases don't just drift aimlessly. Over time, they mix with surrounding hydrogen and helium, seeding the interstellar medium with heavier elements. When new stars form from these clouds, they inherit some of that material. These second-generation stars, known as population 2 stars, have trace amounts of elements like carbon, nitrogen, and oxygen, tiny signatures that tell us they were born into a universe that had already started its chemical transformation. And so the cycle continues. Stars live, burn, and die, returning their matter to space. New stars and planets form from that recycled material, enriched a little more each time. This process of stellar birth, fusion, death, and rebirth is how the universe went from a sparse cloud of simple atoms to one filled with galaxies, complex chemistry, and the building blocks of life. Spectroscopy allows us to trace this entire journey. When we analyze the light from a star, we're not just seeing how hot it is or how fast it's moving. We're seeing what it's made of. Every element in a star's atmosphere leaves behind a unique fingerprint in the spectrum. Those absorption lines tell us, for instance, whether there is calcium or sodium, iron or oxygen. And because we can measure these elements precisely, we can determine how metal-rich a star is. In astronomy, the term metals is a charming simplification that includes every element heavier than helium. A star's metallicity, or its metal content, acts like a cosmic birth certificate. High metallicity means the star formed in a universe that had already gone through many cycles of star formation and death. Low metallicity suggests a more ancient origin. The oldest stars we've found, often located in the halo of our galaxy or in ancient globular clusters, have extremely low metallicities. Some contain only 1 part in 100,000 of heavy elements compared to the Sun. Their light, studied carefully through spectroscopy, reveals a nearly pristine composition, mostly hydrogen and helium, with a trace of later ingredients. These stars are like fossils, preserving the chemistry of the early universe.
By mapping metallicity across the galaxy, astronomers can build a timeline of stellar populations and chemical evolution. Younger stars, especially those in the galactic disk, tend to be more metal-rich. Older stars in the halo or bulge are generally poorer in metals. This gradient tells us how the galaxy assembled itself over billions of years, from the inside out. And this isn't limited to our own galaxy. Spectroscopy allows us to study the chemical composition of stars in nearby galaxies too. We can see how different galaxies evolve at different rates, some building up their heavy elements quickly, others slowly. Even the gas between stars speaks to us through light. Spectroscopy of distant quasars, bright active galactic nuclei powered by supermassive black holes, often reveals absorption lines from intervening clouds of gas. These clouds, sometimes billions of light years away,
leave narrow fingerprints in the light as it passes through them. By studying these lines, we can measure how the chemical composition of the universe has changed over time. What emerges from all this is a picture of a universe in chemical flux. Once composed almost entirely of hydrogen and helium, it has slowly enriched itself through countless cycles of stellar life and death. The elements needed for life, carbon, nitrogen, oxygen, phosphorus, and sulfur, were all forged in the quiet fires of stars and scattered into the cosmos. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it came from stars. We are, quite literally, stardust. And we know this not because we've gathered samples from across the galaxy, but because of light. The light from stars and galaxies carries with it the imprint of the elements they contain. Spectroscopy gives us the tools to decode that imprint, to read the history of cosmic chemistry written across the sky. It's astonishing, really. With just a beam of starlight split through a prism or grating, we can peer back billions of years and watch the universe build itself, atom by atom. So the next time you look at a star, any star, whether brilliant and blue or faint and red, remember, you're not just seeing a point of light. You're seeing the product of cosmic recycling, the ongoing story of how hydrogen became helium, how helium became carbon, and how eventually a universe that began with simplicity learned how to make complexity. And it's still happening, even now. A story written not just in the light of a star, but in the combined glow of an entire galaxy. Chapter 7: The Light of Galaxies. Drift with me now and let your mind expand to a scale so grand it is almost unimaginable. Imagine looking up at the night sky and somehow peeling back the stars, layer by layer, until you find something even grander behind them. Galaxies. Not just a handful, but billions of them. Each one is a sprawling collection of stars, gas, dust, and mystery. Some are neat and spiral-shaped, like celestial pinwheels. Others are rounded and smooth, like giant space potatoes. And a few look like someone shook the cosmos and left the pieces scattered. They're beautiful, complex, and very far away. But even from across billions of light years, galaxies still whisper their secrets to us through light. Galaxies may seem too distant or too large to analyze in the same way we study a single star, but the truth is, we can learn just as much, and sometimes even more, by studying their light. When we spread that light out into a spectrum, it becomes a treasure map of information, revealing not just what the galaxy contains, but what it's doing, how fast it's changing, and how far back in time we're seeing it. To begin with, let's talk about what we see when we look at a galaxy. With the naked eye, most galaxies are faint smudges, if we can see them at all. The Andromeda Galaxy, for instance, is just barely visible under very dark skies. But with a telescope, that smudge transforms into structure: spiral arms, glowing cores, and filaments of dust. What you're seeing is the combined light of hundreds of billions of stars, all packed into a gravitational embrace. Just as with individual stars, that light contains layers of meaning. When we take the spectrum of a galaxy, we're essentially gathering the blended light of everything inside it: stars, gas clouds, nebulae, and sometimes even supermassive black holes. And remarkably, we can separate those ingredients. It's a bit like tasting a complex soup and being able to pick out the garlic, the basil, the tomatoes, and the pinch of pepper just by paying close attention. The first clue a galaxy gives us is its type. Galaxies come in several general flavors: spiral, elliptical, and irregular. Spiral galaxies like our own, the Milky Way and Andromeda, are full of gas and dust and active star formation. They have young, blue stars lighting up their arms and a central bulge of older, redder stars. Elliptical galaxies, on the other hand, are more like giant, smooth orbs. They have used up much of their gas and don't form many new stars. Most of their light comes from older, cooler stellar populations. By analyzing a galaxy's color and spectrum, we can tell what kinds of stars dominate it. Blue-dominated light suggests ongoing star formation and younger stars. Red light usually means an older, quieter galaxy. Speaking of gas, spectroscopy also tells us a lot about the interstellar medium in galaxies. Gas doesn't just sit there quietly, it glows. In regions where stars are forming, young, hot stars pump out ultraviolet light that excites nearby hydrogen atoms. These atoms then emit light as they cool down, especially in the hydrogen alpha line, a deep red signature that astronomers use to trace star-forming regions. When we observe a galaxy in H-alpha, we can map out where new stars are being born. These glowing regions often cluster along the spiral arms where gas is densest. Other spectral lines reveal the presence of heavier elements like oxygen, nitrogen, and sulfur. By comparing the strength of these lines, we can estimate the metallicity of a galaxy, how chemically enriched it is. Galaxies with lots of star formation tend to have more metals, since stars create these elements and spread them through the interstellar medium. This enrichment process is part of a galaxy's ongoing evolution. Now, let's take that light and stretch it across space. The farther a galaxy is, the more its light is redshifted, stretched out as the universe expands. This redshift not only tells us how far away the galaxy is, it also tells us how long ago the light was emitted. When we look at a galaxy that's 5 billion light-years away, we're seeing it as it was 5 billion years ago. Its light has traveled all that time just to reach us, carrying a snapshot of what it looked like before Earth even had oceans. Galaxies at different redshifts show different stages of development. Nearby galaxies are often well-formed, with clear structures and settled populations of stars. But as we look farther back, we start to see galaxies in the midst of their growth. Irregular shapes, wild star formation, and chaotic merges. These are the baby pictures of the universe, and they show us how structure formed and evolved.
And then there are the dramatic ones, the galaxies that light up like cosmic fireworks. These often contain active galactic nuclei, or AGNs. At the heart of almost every large galaxy is a supermassive black hole. Most of the time, these black holes are quiet, but in some galaxies, gas and dust fall into them at such high speeds that the material heats up and emits huge amounts of energy. The result is a luminous, energetic core that can outshine the rest of the galaxy combined. Quasars in particular are some of the brightest objects in the universe, visible from billions of light-years away. And all of their secrets, their mass, their spin, and their rate of feeding are hidden in their light. Spectroscopy helps us untangle that light. We can measure the width of spectral lines to estimate the speed of gas orbiting the black hole. We can detect elements that have been blasted into high energy states. We can even map how the light varies over time, revealing turbulence and motion in the accretion disk. Even galaxies that aren't active still have movement within them. Using the Doppler effect, astronomers can measure how stars and gas are moving inside a galaxy. Light from one side of a rotating galaxy will be blue-shifted as it moves toward us, while light from the other side is red-shifted as it moves away. This allows us to map a galaxy's rotation curve, and surprisingly, that's where one of astronomy's biggest mysteries comes from. When we chart these curves, we find that stars at the outer edges of galaxies are moving far faster than expected, faster than gravity from the visible matter alone should allow. This discrepancy is one of the main pieces of evidence for dark matter, the unseen material that appears to make up most of the mass in the universe. Once again, it's light, not direct observation, that brings this invisible force to our attention. The more we study starlight from galaxies, the more layers of meaning we uncover. It tells us how galaxies live, how they grow, and how they sometimes collide and merge. It reveals bursts of star formation, quiescent periods of aging, and the tumultuous influence of black holes. And the distances involved are staggering. Some of the galaxies we've studied in detail are over 10 billion light-years away. Their light began its journey when the universe was still a toddler. Yet here it is, arriving in our detectors, carrying all the information we need to learn about those ancient times. Galaxies may be faraway cities of stars, but their light is immediate. It falls on our telescopes, flows into our spectrometers, and prints its story in fine spectral lines. We don't need to travel to those galaxies to understand them. We just need to pay close attention to what their light is saying. And in the silence of space, that light never stops speaking. And that quiet conversation continues even at the very end, in the blinding flash of a stellar death.
Chapter 8: The Aftermath of Light. Drift with me now into a story of an ending. There is something deeply poetic about the way a star concludes its life. After millions or even billions of years of steady burning, fusing, glowing, and radiating gently into the cosmos, it doesn't simply fade away. Some stars go out with a bang so powerful it can outshine an entire galaxy for weeks. A supernova is not just a dramatic finale. It's an explosion so energetic that it shakes the very fabric of space, tears atoms apart, builds new ones, and launches them across the galaxy at thousands of kilometers per second. And as always, the key to understanding it all is light. When a star explodes, its light doesn't simply turn on and off. The brightness rises sharply, then slowly fades over days, weeks, or even months. But if you look beyond the blinding glow and break that light into a spectrum, what you'll see is something even more astonishing. A story unfolding in color and line, a moment-by-moment record of nuclear chaos, elemental creation, and cosmic recycling. Supernova come in several types, but the two most well-known are Type 1 and Type 2. Each has its own signature, both in its behavior and in its spectrum. Type 1 supernova occur when a massive star, at least 8 times the mass of our Sun, reaches the end of its fuel supply. The core collapses, gravity wins the battle, and the result is a catastrophic explosion. Hydrogen features prominently in these spectra, since the outer layers of the star still contain large amounts of it. In contrast, Type Ia supernova don't come from single massive stars, but from white dwarfs in binary systems. A white dwarf can steal matter from its companion star until it reaches a critical mass, at which point it undergoes a thermonuclear explosion. These explosions tend to show little or no hydrogen in their spectra, but they do exhibit strong silicon lines early on. The difference matters because the type of supernova tells us not only how the explosion happened, but also what elements are likely to be produced and ejected into space. And we figure all of this out not from the brightness alone, but from the way the spectral lines behave before, during, and after the blast. When a supernova first erupts, it reaches its peak brightness in a matter of days. The early spectrum is dominated by broad, smeared-out absorption lines. These lines aren't sharp and well-defined like those you might see in the spectrum of a stable star. They're widened and distorted due to the high speeds involved. The outer layers of a supernova can expand at tens of thousands of kilometers per second, and that rapid motion stretches the light into a wide, shallow trough in the spectrum. That broadening tells us just how fast the material is moving. For Type 2 supernova, one of the most striking features is the hydrogen alpha line. It's the same deep red line we see in nebula and star-forming regions, but here it's broadened and distorted by the extreme dynamics of the explosion. As the blast progresses, the light changes. For type Ia supernova, the early spectra often shows strong lines of singly ionized silicon, a reliable fingerprint used to identify this specific type. The presence of silicon, along with the absence of hydrogen, is a dead giveaway that we're looking at a white dwarf explosion. Over time, as the supernova cools and the outer layers thin out, lines from iron, nickel, and cobalt emerge, elements formed in the heart of the detonation. These heavier elements aren't just floating around, they are being forged in real time through a process called nucleosynthesis. During the explosion, temperatures rise so high into the billions of degrees that atomic nuclei are smashed together, building new elements atom by atom. The very iron in your blood and the calcium in your bones were likely created this way in some ancient supernova that exploded long before Earth existed. By taking spectra at different times during the supernova's evolution, astronomers can build a kind of chemical timeline. Early on, the light is dominated by the surface material. As time passes, deeper layers become visible and new lines begin to dominate. You can see the quiet transition from silicon and sulfur to iron and cobalt. Each element appears at a different phase, like actors entering the stage on cue, each one playing a crucial role in the grand finale.
And then there's the nebula phase. After the supernova has faded from its blinding peak and the material has expanded into space, the spectrum changes again. The light now comes from glowing gas heated by radioactive decay. In particular, the decay of nickel into cobalt and then into iron provides energy that keeps the remnant glowing long after the explosion has passed. During this phase, emission lines become more prominent. Unlike the earlier absorption-dominated spectra, nebula spectra are filled with bright, sharp emission features. These lines allow astronomers to determine not just which elements are present, but also how they're distributed in the expanding cloud. Sometimes we even see forbidden lines, transitions that aren't allowed under normal laboratory conditions on Earth because they occur so slowly that collisions would interrupt them. But in the thin, low-density environment of a supernova remnant, these lines can occur. Their presence helps identify elements like oxygen, neon, and sulfur in the cooling cloud. They are called forbidden not because they are breaking any rules, but because they're just very shy, visible only in the quiet solitude of space. All of this, from the blinding flash of the explosion to the faint whisper of a cooling remnant, is captured in light. And not just any light, but structured, detailed, exquisitely informative spectra. They don't just tell us what blew up, they tell us how and when and what was created in the process. In the end, a supernova is both an ending and a beginning. It marks the death of a star, but also the birth of new elements, new possibilities, and perhaps even new solar systems. And long after the blast has faded, its story lives on in the spectral fingerprints it leaves behind. Still glowing, still telling the universe what it became. It is a slow, patient, and quiet way for the cosmos to write its history. A story in which even a whisper of light is a profound and ancient message. Chapter 9. The Time Capsule of Light. Drift with me now and consider a final, most profound quality of light. It is many things: a wave, a particle, a carrier of energy, a painter of sunsets. But perhaps one of its most curious qualities is that it is always running late. Not because it's slow, it's actually the fastest thing there is, but because space is just that vast. The distances between stars and galaxies are so enormous that even light, racing along at nearly 300,000 kilometers per second, takes its sweet time getting to us. And that simple, elegant delay turns our telescopes into time machines. It sounds like science fiction, but it is pure, elegant fact.
When you look into the night sky, you are literally looking into the past. The farther away something is, the longer its light has taken to reach you, and the older the picture you're seeing. It's as if the universe has left a trail of old postcards, each one traveling at light speed, arriving on Earth in a steady stream and saying, "Here's what I look like when I sent this." When you gaze at the moon, you're seeing it as it was about 1.3 seconds ago. That's how long it takes for moonlight, actually reflected sunlight, to travel the roughly 384,000 kilometers to Earth. When you look at the sun, you're seeing it 8 minutes and 20 seconds in the past. If the sun were to mysteriously vanish right now, we wouldn't notice for over 8 minutes. But as you look farther out, the numbers begin to stretch dramatically. The nearest star system, Alpha Centauri, is about 4 light years away. That's 4 years of travel time for its light to reach us. If you could somehow watch a planet orbiting one of those stars, you'd be watching a recording from 4 years ago, not a live feed. This delay turns into something truly extraordinary when we point our telescopes beyond our local neighborhood. The Andromeda Galaxy, our nearest major galactic neighbor, is about 2.5 million light-years away. That's 2.5 million years of travel time for its light to reach us. The image we see of Andromeda is what it looked like back when early human ancestors were first experimenting with stone tools. Push the telescope deeper into space, and we reach even further back in time. Some of the galaxies detected by the James Webb Space Telescope are over 13 billion light-years away. Their light began its journey when the universe was less than 5% of its current age. The cosmos was still in its childhood, hotter, denser, and more chaotic than the gentle spirals and elliptical galaxies we see today. This concept is one of the most mind-stretching and delightful aspects of astronomy. The sky is not just a spatial map, it's a temporal map. Looking up is also looking back. Every dot of light, every fuzzy galaxy, every faint smudge in the black is a message from the past. And every telescope, no matter how small or mighty, is a kind of time traveler, collecting ancient photons and translating them into a cosmic history book. What makes this even more remarkable is how precise this fossil record can be. Because light carries information not just about brightness, but about wavelength, composition, and motion, we can use it to study what things were like billions of years ago with surprising clarity. Light from early galaxies tells us how stars formed when the universe was young. It shows us the first heavy elements forged in stellar furnaces. It lets us see cosmic structures assembling like bricks in a slowly rising cathedral.
When we look at the most distant galaxies, we're peering into a time when the first stars were igniting. These primordial stars, massive and short-lived, are thought to have formed from pristine clouds of hydrogen and helium left over from the Big Bang. Their light, stretched and redshifted by the expansion of the universe, arrives at Earth after a journey of billions of years. That light doesn't just show us where those stars were, it shows us what the universe itself was becoming. This is why astronomers talk about look-back time. It's a way of measuring not just distance, but age. A galaxy 10 billion light-years away is seen as it was 10 billion years ago. A quasar from 12 billion light-years away is a time capsule from an era when galaxies were just beginning to take shape. The cosmic microwave background, the faint afterglow of the Big Bang itself, is the oldest light we can observe, dating back over 13.8 billion years. It's the universe's baby picture, and it fills the sky with a quiet whisper of ancient heat. In this way, astronomy becomes a kind of cosmic archaeology. Just as paleontologists dig through rock layers to uncover fossils from Earth's distant past, astronomers sift through layers of light, each one older than the last. The difference is that their tools are not shovels and brushes, but mirrors, lenses, and spectrometers. They don't uncover bones, they uncover photons, and every photon carries a clue. This concept brings a strange kind of intimacy to the universe. We're not just seeing distant places, we're witnessing ancient moments. The light from a galaxy 10 billion light years away is arriving now, in your lifetime, after traveling undisturbed through the void since before the Earth had oceans. It's as if the cosmos is gently handing you a story it has been carrying for eons. And perhaps most wonderfully, this story is still being written. The universe continues to shine, to evolve, to send out photons that will someday reach distant observers in some future epoch. Maybe a civilization a billion years from now will study the light from our galaxy as it looks today. To them, we'll be a deep sky object glowing softly from across time. So, as you drift off tonight, perhaps you'll think of starlight a little differently, not just as a sparkle or a shimmer, but as a message sent long ago, still traveling through space to find you. It's the universe whispering its story, one photon at a time. The stars will keep shining. They are always on their way to meet us.